In this presentation, we will discuss force and the importance of force as we think about motion and how the motion of an object changes. So, thinking back to some of the things that you've learned before about motion, we know that the motion of an object can be described in terms of its speed, its velocity, its acceleration, its displacement, its distance covered, and all of those descriptions of motion are described in terms of kinematics. And now the focus that we're going to move to is dynamics, which is the other aspect of describing motion. And dynamics explains why objects move or have a change in the motion. So kinematics is the how of the motion change, and dynamics is the why. And so in order to understand dynamics, one of the things that's important when we look at the motion of an object changing is this idea of a force. And a force, a very basic definition of force, is a push or a pull. And we learn this really, early on in our, academic careers, or even as kids. You want to push on a swing to go higher, and so on. So it turns out there's two classifications of forces. There's contact forces and non-contact forces. The non-contact forces are forces that act at a distance, and the objects don't actually have to be touching one another. And some examples of those that we're actually probably very, very familiar with are magnetic forces. So you can have magnets exert forces on one another without actually having the magnets touch one another. You could bring two magnets near one another and they'll exert forces. Another example is electrical charge. You can have charges that exert forces on one another and they don't actually have to be touching. So a good example of this would be if you were to rub a balloon in your hair and it would accumulate some charge, and then you could put it near your hair and it would actually cause your hair to be attracted to the balloon, and they don't actually have to be touching for that attraction to occur. And then we also have what's called a gravitational force, which is the force between masses. So any two masses in the universe actually exert forces on one another, and it's an attractive type of force. All non-contact forces are called field forces because we say that there's a field associated with them. So a magnet has a magnetic field. A charge has an electric field associated with it, and masses have gravitational fields associated with them. And field is basically just saying that objects can exert forces on one another over some distance, that there's some field around those forces. There's other types of forces called contact forces. Those are the ones that we're most familiar with. That's where objects actually have to touch one another in order to exert forces on one another. So here we have a spring where a hand is pulling on a spring, it's exerting a force on a spring. We've got someone pulling a wagon, they have to be touching the handle of the wagon. And then we've got the football player kicking the football, and there has to be physical contact with the football in order for that football to actually move. So it turns out that early on in Aristotle's time, Aristotle was a very famous philosopher of his time, that he described motion in a way that was completely incorrect. But what he did is he viewed the world around him. He's a philosopher, and so he viewed the world around him, he looked at what was going on with motion, and then he drew conclusions from what he observed. And what he observed in nature was that the natural state of an object near the surface of the earth is to be at rest. And so if you look around, you see objects, they're not usually in motion, right? They're usually sitting there. So that was his first assumption, and it's actually incorrect. And then the second assumption that he made was that a force, and I don't think he used the word force, but a push or a pull is required to maintain the motion of an object. So if you want to get an object moving and keep it moving over a surface, let's say we're pushing a crate across the floor in the science building, then we have to keep applying a force in order to keep that object moving at a constant speed. And that's also incorrect. And so, but Aristotle was basically looking at what he saw happening in the universe, and this is the way we see things, and so that's the way that he was describing things. And then Galileo came along much, much later, and he was an astronomer, a physicist, and actually also an engineer. And he looked at motion again. And what he discovered is that the natural state of an object near the surface of the Earth is to travel at a constant speed in a straight line or to be at rest. And it turns out that those two states of an object, rest or moving at a constant speed in a straight line, are actually equivalent to one another. And we're going to see how that works in just a little bit. He also discovered that a force actually is required to change the motion of an object, but it's not required to maintain the motion of an object. The best example I can think of this is if you take a puck on an ice hockey rink and you give it a slight push at one end of the ice hockey rink, that puck will actually travel all the way across the rink, essentially traveling at a constant speed. So a force was required to change the motion. The puck was at rest, you gave it a push and it started to move, but once it was in motion, it continued to move at a constant velocity across the ice. So what's the big difference between Galileo and Aristotle? So, well, Galileo was a scientist, and he actually performed experiments to test these hypotheses that he had, where Aristotle just made these assumptions based on what he saw, but he never actually performed experiments. So Galileo is thought to be the father of the scientific method. And so one of the experiments that Galileo did to test these hypotheses that he had was to take a ball and roll it down a ramp, and then it would go across a flat surface, and then he had another ramp on the other side. And so what he discovered is that if you roll the ball down the ramp, you release it, it's going to go to the same height on the other side of the ramp, and then of course it would start to go back down. And so you could imagine that in the first picture, those ramps are essentially the same angle incline. But you could have another situation where the ramp on the other side is actually not at as steep of an incline. And what he discovered is that that ball would still roll up to the same height that it was released from. So then you could imagine that you take that ramp and you make it so that it's flat. And so you release this object and it goes down the ramp. And the question is, where is the final position? Well, where is it going to stop? Well, it's not going to stop, right? It's going to keep on going at a constant speed until it reaches another ramp and it can slow down. So the ball obviously speeds up on the way down the incline due to gravity acting on it, and then it slows down going back up the ramp because gravity is pulling it back down. Of course, along the, there's a component of gravity along the incline that's slowing it down. So, so these ideas that he had of performing experiments were some of the first of his time. And so it turns out that Galileo was correct. And so we could kind of conclude from Galileo that a force is required to change the motion of an object. It's not required to maintain the motion. So remember, if I go back over here, this ball would go down the incline. When it got to the flat surface, it would continue to move at a constant speed in a straight line unless there's some type of force that's acting on it. And we can change the motion of an object in a number of different ways. We can cause the object to speed up. We can cause the object to slow down. We can cause the object to change direction. That's a change in the motion. Or we could actually have the object change speed and direction. So speeding up and slowing down is pretty easy to imagine. Changing direction might be that you're in your car and you're going around a turn. You could be going around that turn at a constant speed, so your car is changing direction but not speed. Or you could be going around that turn with a constant, or with a speed that's changing. You could be slowing down and going around a turn, and that would be changing speed and direction. So all of these descriptions of changing motion, speeding up, slowing down, changing direction, are all described in terms of acceleration. So there must be some relationship between the force that's being applied on an object and how much that object actually is going to change its motion or accelerate. So here's a thought experiment. Suppose that I have a physics textbook and I have a crate that's filled with bricks. And I apply the same force on both of these objects, and suppose that they are on ice, right? So it's very slippery, and there's no, I know we haven't talked about friction, but there's no friction, so they'll move very easily if you push them. What can we say about the motion of each one of these? Are they going to move the same way, or is it going to be easier to move one versus the other? And so the answer is that the textbook, which obviously has less mass associated with it, is going to be much easier to move than this crate that's filled with bricks. And so the physics textbook is going to have a larger change in motion as compared to the smaller change in motion of the crate. And another, well, we'll talk about that. I was going to think of another example, but I have another example for later. So here are two videos, or two little motion diagrams for an object. The top picture, the crate, has a mass of 10 kilograms and a force is being applied. Now, I know we haven't talked about the size or the units for force, but this is 10 newtons here for an applied force, and this one is 10. So they both have the same force being applied, but the motion is going to be different. So I'm going to go ahead and play the video. See if I can do this. I think I'm going to have to do this. So let me play the first one, and you can watch the motion of the crate. All right, and the video stops. Now, when we have a larger mass, same force is applied. Let's look at the motion of the crate and see if the motion is the same. It's hard to tell, but that crate is actually speeding up as it goes, but it's certainly not speeding up at the same rate as the first object. So the force applied on the object is going to have an impact on the motion. They both started from rest. They both changed their motion, but they changed their motion differently based on what their mass was. So if we sort of think about the findings of Galileo, he realized that a force causes a change in the motion, that the same force applied to different objects causes different results, which we just saw. And so the conclusion there is that every object has some resistance to change in motion. So the 100 kilogram crate, the bottom figure, had a larger resistance to change in its motion versus the 10 kilogram crate in the first picture. So we defined this tendency of an object to remain at rest or in motion at a constant speed in a straight line. Got a bit of a spelling error there, sorry. In a straight line is defined as inertia. So inertia is basically measuring an object's resistance to change. And we can measure an object's resistance to change by measuring the mass of the object. So the larger the mass of the object is, the larger its inertia is, and the greater tendency that object has to remain at rest or in motion at a constant speed in a straight line. So an example that I always sort of like to give with inertia is this idea of cars traveling down a road. And I always think about logging trucks because where I live, there's a lot of logging trucks. And then I typically also like to sort of compare a logging truck to like a Volkswagen Bug. And Volkswagens, or those little bug cars, are very small. So the logging truck filled with logs is going to have a very large mass, and the Volkswagen Bug is going to have a smaller mass. And suppose they're both traveling at 55 miles an hour down a highway, and they're traveling side by side, and they both see a stoplight up ahead and they have to stop, so they hit the brakes. Which one of these is going to be more difficult to change the motion of, right? So they're both traveling at a constant speed. We want to change the motion so that they're at rest. And the answer, of course, is the logging truck, right? If you had two of these vehicles behind you and you were in your car, you'd feel much more comfortable if that Volkswagen Bug was behind you versus that logging truck that had to stop very quickly. So inertia is just basically a measure of an object's resistance to change. If an object has a lot of mass, it's going to be harder to change its motion. It's going to have a lot of inertia associated with it. Now, oftentimes there's some confusion with the difference between mass and the weight of an object, and a lot of times people will use those two values, those two properties interchangeably, and they're really not interchangeable. So mass is an intrinsic property of all matter. So that means that it's made, matter is made up of mass. It's not something that that we can necessarily change. If you have a particular object and you look at that object and you measure its mass, it's made up of protons, neutrons, electrons, and so how much matter you have is what that mass is measuring. The mass does not depend on the physical location of the object. So if you measured the mass of an object on the Earth and you measured the mass of an object on the moon, or you measured the mass of an object out in space, they would all have exactly the same mass. And that's harder for people to understand because if you're on the moon, you have less gravity, but we'll get to that. I think a good way to imagine measuring mass is to imagine if you had a tennis ball versus one of those workout medicine balls. Hopefully you're all familiar with those. Those are like really heavy balls that you can use to do exercise with, sit-ups and so on. So you can measure, you can tell the difference in their mass even if gravity wasn't present. If you were out in space, if you took the tennis ball in your hand out in space and you shook it, you would feel some resistance to changing the motion of the tennis ball. But if you took that medicine ball, even out in space, and you tried to shake that medicine ball, you would have more resistance to changing the motion of the medicine ball, even out in space without any gravity present. So that means that it has more mass, it has more resistance to change. The units that we use for mass in physics are kilograms, but oftentimes in a lab setting we have to measure things in grams because a kilogram is a pretty large number. So 1 kilogram is equal to 1,000 grams, but the standard units that we always use for mass are kilograms. Now weight is something different. The weight of an object is actually the force that's exerted on the object due to the gravitational pull of a particular celestial object. So on the Earth, we have a weight because the Earth is actually pulling on us, and we experience a force due to that gravitational pull, and that's why we have a weight here on the Earth. If we went to the moon, we would experience a different gravitational pull on the moon, and therefore we would have a different weight on the moon. So weight does depend on physical location, depends on where you are, what the celestial object you're located on. And the standard units that we use for weight are the units that we're going to use for force. And we haven't talked about what those units are yet, but the standard unit for weight in physics is going to be newtons. There are other units that we use. So in the United States, we use pounds for our weight. And so pound is also another unit that we could use for force. But the big thing is there is a difference between mass and weight. Mass, intrinsic property, doesn't change no matter where you're located, versus weight that does change based on the gravity that you are experiencing where you're located. The good thing is that mass and weight are directly proportional to one another based on the gravity of the planet or the celestial body that you're on. So if an object has a larger mass, it's also going to have a larger weight, and vice versa on a particular planet. So we can see how they are related to one another. Suppose that you have that 1 kilogram textbook, and its weight on the Earth and its weight on the moon. And we want to know, how do they compare to one another? So it turns out that if you were to weigh a 1 kilogram textbook on the Earth, it would weigh 10 newtons, and more accurately 9.8. And that 9.8 should be familiar because 9.8 is used for gravitational acceleration, 9.8 meters per second squared, and that's not coincidental. If we were to take that same textbook and measure it on the moon, it would measure about 1.67 newtons on the moon. So there's less gravity on the moon, and therefore the weight would be different. The mass doesn't change. So if we measured the mass on the Earth, it would be 1 kilogram. If we measured the mass on the moon, it would also be 1 kilogram. Just to give a feel for what 1 kilogram is equal to, so on the Earth, which is what we're most familiar with, 1 kilogram is equivalent to a force of 10 newtons in terms of the gravitational pull, and that's equivalent to about 2.2 pounds. So we can have some idea of what a newton, is equivalent to in terms of pounds. We could ask the same question, how much would a 2 kilogram textbook weigh on each location? Well, if there's 2 kilograms and the mass is proportional to the weight, then I had 1 kilogram, I would just double it. So the amount that the textbook would weigh, 2 kilogram textbook would weigh on the Earth would be 20 newtons. And on the moon, it would be double 1.67. So it turns out that there is a formula that we can use to calculate what the weight of an object is if we know what the mass of the object is. And the weight of an object, which is the gravitational force that that object experiences, is equal to the mass of the object times the gravitational acceleration of the object, the gravitational acceleration of the body, the celestial body that you're on. So if we were on Earth, then Earth's gravity for g would be 9.8, and we've been using 10 meters per second squared. If we were on the moon, moon's gravity is about a sixth Earth's gravity, which is about 1.63. If you use 10, it's about 1.67. And then we could look at other, celestial bodies. So if we went to Mars, Mars has a greater gravitational acceleration than the moon, but it's still very much smaller, quite a bit smaller than the Earth. And then if we went to Jupiter, we have a much larger gravitational acceleration, so our weight would be much more than if we were on the Earth. So we could look at a simple example. Suppose that we have a 50 kilogram child, and we want to know what is the weight or the force of gravity of that 50 kilogram child on the Earth. So what does that child weigh on the Earth? So we know that the weight of the object, or the force of gravity, is the mass times gravity. So it's 50 kilograms times 10 meters per second squared. So that child would weigh 500 newtons on the Earth. If we were interested in what that's equal to in pounds, we know that 10 newtons is about 2.2 pounds. So if I multiplied by 2.2 and divide by 10 in order to cancel out my units, that's about 110 pounds. So that gives you a feel for what, you could kind of see, what your weight is in pounds and what that's equivalent to in terms of newtons and kilograms.